Okay, great. So it's my pleasure to welcome our next speaker, Victor Shrira, who will talk about a novel, essentially 2D evolution equation for long-wave patterns in boundary layers.
Just 1 second. So, could you hear me? Do you see the screen?
We can hear you, Victor. Yes.
Yeah. Great. Okay. So first, my gratitude to the organizers for the invitation. It's proved to be a really exciting meeting, which I enjoyed. And so the title of my talk is here, and the work is most of the work was done with my PhD student Joseph Ol. So what it will be about? Evolution equations, nonlinear evolution equations are one of the key tools in our toolbox for understanding of nature. And most of the known evolution equations are one-dimensional PDEs like KdV, Burgers, and LS. These universal equations crop out everywhere and often have weakly 2D extension. There are very few known essentially 2D evolution equations. One of the examples is Zakharov-Kuznetsov equation. So my main physical motivation for this work is first that boundary layers are everywhere in nature and engineering context, and observations of laminar tubular transition exhibit a variety of coherency patterns, which the physics of which is not understood. And what we show that the boundary layers, dynamics of the boundary layer provides an inexhaustible source of new, essentially 2D pseudo-differential equations. So these are examples of coherent patterns observed in transition in wind tunnels. So this is snapshots at 2 different moments, and this is a longitudinal component of perturbation velocity. So how the talk is organized? I will speak first, introduce what we need to know about boundary layers and what kind of boundary layer we will look. So introduce the concept of vorticity waves, which might help. Then I outline asymptotic derivation of evolution equation for the simplest case, discuss the collapses this equation support, and then discuss generalizations and conclusions. So let's start. So this is a schematic of a typical boundary layer, and when we approximate this boundary layer by piecewise linear way, so at the interface we get this vorticity wave. So if we have smooth boundary, then it's the mode doesn't disappear. It's and there are still discrete weakly decaying modes, and these modes, the starting point that these discrete modes could be treated as waves, and these sometimes are referred to as vorticity waves. We focus on the linear evolution of these linear decaying modes. So to avoid confusion, notation and convention differ for different types of boundary layers. For free surface boundary layers, usually the flow has maximum at the boundary and 0 at infinity. And for more commonly in the, say, the internal context, so it is 0 at the boundary and some tends to some constant free stream velocity at infinity. So what kind of extensions we will also consider? So we could add one more wall, and that will be confined boundary layer. We could add stratification into boundary layer. It will be, and this will be weakly stratified boundary layer. The boundary layer could have two components, two comparable components of velocity, and that will be 3D boundary layers. And the boundary could be not necessarily rigid, but could be elastic. And this gives one more direction of generalization. And the flow could be, and the outer flow could be also stratified and okay. And we will consider all this. So the asymptotic, so we start with the full Navier-Stokes equations, which I do not show here. And we introduce small parameters, waves. We consider waves long compared to the boundary layer thickness d, and with kx and ky comparable. The waves are of small but finite amplitude, and Reynolds number is large. The specific scaling we take is as follows, and we'll look for solution in the form of a asymptotic series in epsilon. So we use the standard in fluid dynamics triple deck approach. So we have 3 different domains where solutions are very different. So this is the main, this inside the boundary layer is called sometimes main deck, and there is outer flow where flow is essentially inviscid, and there is viscous sublayer. It also coincides in our problem with critical layer, which is very thin compared to the boundary layer width. So using multiple scales in the boundary layer and the main deck, we look for solution in the form of this expansion in epsilon. And to leading order in Fourier space with respect, so in leading order, system becomes linear, and in Fourier space, with respect to x, y, and t, the Navier-Stokes equations reduce to Rayleigh equation with in Z. And this in general, we could write down a general solution, but crucially to leading order, the dependence on the fast vertical scale Z separates. This is what is written here. So this is the way, so there is this fast dependence on Z, fast, that's on the scale of boundary layer. So there is some amplitude A, which depends on slow x and y, and slow time, and there is also some function which this is in convolution. So A has physical sense of the amplitude of longitudinal component of velocity, and x and y here I expect effectively x1 and u1, that's epsilon variable scale of epsilon minus 1, and zeta here is stretched, and tau are epsilon square stretched vertical coordinate and time t. Knowing A, we can find other components of the field. And so now we focus on deriving an evolution equation for A. So in the to leading order, longitudinal velocity could be written like that, and span-wise velocity is 0 in leading order. So the next order, by solving the resulting in homogeneous Rayleigh equation with the right-hand side due to dispersion, nonlinearity, and viscous terms, and upon finding explicit dependence on slow Z and satisfying boundary conditions, we, after lengthy algebra, obtain this equation. So these terms do not require comment. So what is K? K is pseudo-differential operator, which could be written like this, or in Fourier space in terms of double Fourier direct and inverse Fourier transform, it looks like that. So this, to make it transparent, it corresponds to dispersion proportional to modulus of k, where k is two-dimensional wave vector. And this is essentially two-dimensional generalization of the boundary of the Benjamin-Onno equation with the Rayleigh friction term. This is the Rayleigh friction term. So not is kind of perfect with this expansion. So the higher order terms start to diverge near the boundary and in the critical layer, and we need to handle this. So to this end, we choose different variables, expand there, solve Navier-Stokes equation there, and then match them to this solution in the main deck. So I skip this. This is the most labor-intensive and challenging part of the derivation. And so what is, I give just a brief summary of what it gives. So under adopted assumptions, critical layer is dominated by viscosity and is linear to leading order, but nonlinearity is still important for matching. And the main outcome of the length analysis is that it is possible to find solution of the Navier-Stokes which satisfy boundary conditions and crucially match the main deck solution. And the overall conclusion is that critical layer dynamics doesn't affect the dynamics in the main deck, and hence the evolution equations. Okay, so now we come to the collapse within this equation. So we set for the time being gamma to be zero. This and what is collapse? For nonlinear waves, the term collapse was coined by Zakharov in '72, and the term has roots in astrophysics, where it was used to describe the violent end of life of a star. In wave context, collapse means formation of singularity in finite time with simultaneous shrinkage of the spatial scale. So what happens within framework of this equation? All plane wave solutions are unstable with respect to long wave transverse modulation. That was found in '94. This equation also support axisymmetric steady 2D solitary type solutions, and these solutions are also always unstable. Dyachenko and Kuznetsov showed that this two-dimensional Benjamin-Onno can be presented in this Hamiltonian form with this Hamiltonian, and Hamiltonian can be negative, and it is not bounded from below when amplitude increases. And it has been rigorously proved that for the localized initial condition with negative Hamiltonian, that is with H less than 0, the sufficient, this is the sufficient condition for collapse. And this work, explicit collapse transformation for quasi-planar initial condition was found within the framework of the Witten equations. So what we could get from all this? So first, we could get, we take initial condition with some parameters, and we could see which ones will collapse and which not. So we have boundary kind of neutral boundary of basin of attraction of collapse. Collapse is an attractor. So these curves separate domains of collapse and decay on this form of initial conditions contains just three parameters. A, sigma, amplitude A, scale sigma and elongation alpha. So for symmetric pulses, this is a red curve. So everything is above is collapsing, everything below is decaying. So if we stretch a pulse in lateral direction, so the threshold decreases. If we stretch it streamwise, the threshold goes up. So this is a sample of numerical simulation of collapse. How does it look for a pulse? Its simulation was done by using pseudospectral method. Okay. So here the snapshots of the evolution. The upper panel shows transactions at the height 5% below the maximum, and below seconds of plots shows the transactions with equidistant curves. Okay, so what we could see here that with time, so at least near the maximum, everything becomes symmetric, axially symmetric, and this suggests that existence of self-similar solution, and indeed there is a self-similar solution in this form, and the checked variable x and tau are the distance to singularity, and the function g is given by this equation. Okay, how well this self-similar solution captures what we see numerically. So here we show that in blue shown that amplitude of collapsing solution, like I showed previously, and here is in red, dashed red line, I showed the self-similar solution. It is clear that near this, in the vicinity of singularity, the matching is nearly perfect. So what happens if we now retain non-zero gamma? So here are simulations of result of simulations of amplitudes, simulations for 3 different values of gamma, and we could see that collapses do happen, and gamma increases the threshold and delays the collapse, and but the kind of behavior near in the vicinity of singularity remains the same. So it's not affected by Rayleigh friction. Okay, so now we come to generalization. So first we assume that boundary layer is weakly stratified, and the stratification is epsilon strong, epsilon weak. So then a similar procedure will give us a new evolution equation, and this is new new dispersion term due to this stratification. It is given by this pseudo-differential operator, and and this is yet another essentially two-dimensional generalization of the Benjamin-Onner equation. So we could again plot these boundaries of basing of attractor in space of initial conditions for the symmetric Gaussian pulses, and this is and here the sequence of curves, and here we increase when we increase stratification. 0 is red curve is zero stratification. So understandably, so the threshold of collapse goes up. So this is animation of collapse for stratified boundary layer, and so the difference is in the shapes of cross sections are much more rich, but I will not have time to discuss this. So what will happen if we add one extra boundary? And then our so differential operator will change to this one, and this is a funny equation. It's two-dimensional intermediate long wave equation, and in the limit and it has parameter d, and this distance between two boundaries. When d tends to infinity, it reduces to 2D Benjamin-Ono we just discussed, and the limit of small d, it reduces to the Zakharov-Kuznetsov equation. And 2D Benjamin-Ono supports collapses, and 2D Zakharov-Kuznetsov does not. What happens? So we could write the Hamiltonian and study this neutral curve, and what we could see is that as d tends to 0, there's a Zakharov-Kuznetsov limit. The threshold tends to infinity, but the singularity remains the same as in the 2D Benjamin-Ono. Okay, so this is a major generalization that the flow could have two components of velocity, comparable velocity, the boundary layer. And applying the same asymptotic procedure leads us to this equation. This equation doesn't look at first glance particularly very helpful, because it has two nonlinear terms, and it's not clear what to do with it. So, but which introduce new independent variables in such a way that zeta and eta, and for certainty we choose values of coefficients to be alpha 1 to be equal to delta, and then we come to somewhat familiar form of this equation. So this is one-dimensional nonlinear term, and here we have a different form of non-local operator, which is this. And again, we can find what we did before, the boundaries of Bayesian of attraction, and this is typical for Gauss. This is just for one Gaussian pulse initial, and this is example of collapse. Okay, so the next generalization is so far all the boundaries were considered to be fixed, and now the boundary could be elastic, and that could add new dispersion. So for the example of boundary layer with free surface allowing gravity and capillary waves to propagate, so we have this boundary condition, and we do the same mechanics, and we get similar equation with additional new dispersion. And this is all our old dispersion, and this is the new term we got. So where C1 is the correction to the phase velocity of long vorticity waves due to fluid-induced distortion of the free surface. And so this system also allows collapses. and there is almost infinite possibility to consider different elastic boundaries. Okay, so now there is the last extension I consider, this stratified outer flow, and then I will give it some kernel Q of k. The Q of k is not given explicitly. It's derivative with respect to zeta of function f, where function f is given by this boundary value problem. So the dispersion is specified implicitly by this boundary value problem, and at the moment here we cannot handle it analytically, and we're able to find collapses only numerically. I'm coming to conclusions. So in the context of boundary layer dynamics, we've developed a general approach to derivation of 2+1 pseudo-differential nonlinear evolution equations, which describe dynamics of 3D long wave perturbation for a wide class of boundary layers. The equations are universal in the sense that the details of boundary layer do not matter much. And we show that a wide class of initial conditions evolves into growing coherent structures. These 3D patterns collapse, forming point singularity, at least within the framework of the derived equations. And the vicinity of singularity, these 3D patterns become axially symmetric for any asymmetry of the initial conditions. And the collapse is well described by self-similar solutions. The collapses are, for collapse to occur, the initial perturbation have to exceed a certain threshold, and we can find analytically the boundary in the parameter space separating initial conditions leading to collapse, the basing of attraction for very large Reynolds number, and in other situations we could find it only numerically. We also expect similar collapses to occur in the turbulent boundary layers as well, and the derivation would remain the same, provided the constant eddy viscosity closure hypothesis is justified. That remains to be verified. And the account of weak stratification and stronger dissipation does not prohibit collapses in principle, but it raises the threshold sometimes quite significantly. Thank you.
Thank you very much, Victor. Do we have any question for Victor? So do not hesitate to write in the chat or raise your hand.
Can I ask a question?
Yes, please.
Okay, Victor, very interesting talk. So just to understand, you have whole of situation with collapses. Basically, you claim that all these terms which you add in different conditions, they all correspond to some potential experimental situation, or some of them more mathematical.
What I claim that all these terms I derived correspond to some real physical situations.
Mm-hmm.
So yeah,
also,
this is.
And also your definition of supercritical. I think this case is
this is a mix of different jargons. So in the stability theory, so what where you have should go above threshold, this is supercritical, but this is not terminology from collapse.
Okay, okay, I got your message. Mm-hmm. Thank you.
Okay, so I see that there is no other questions, so maybe we can have a break. So thank you again very much, Victor, for your talk.